Okay, AP Calculus AB. This is the Unit 1, Day 3 warm-up and notes. So this is a warm-up. You should try it on your own first. A little review from some of the things that we were doing in the last homework. Also, I might throw in a couple new challenging problems, but try your best. And so pause the video, and then after you've tried them all, unpause it, and I will go over them. You can check your answers and figure out what you got stuck. Okay? So the first one is, let's see, we're going to convert these to rational form. Now the first one is terminating. So it's easy to be like, well, this is tenths, hundredths, thousandths, 345 thousandths. And, that's a possible answer. We could reduce it. We could take, I think, a 5 easily out of both of these, right? 5 goes in 20, 69 over 200. And I think that's as good as we could do. Next one is repeating decimals. So we set it equal to n. We multiply by 10 to the power of the number of repeating decimals. So there's 3 repeating digits. So it's going to be 10 to the third. So that's 1,000 on both sides. That moves the decimal place 3 spots. And then we have the repeating part still there. And we want it to, we're going to subtract the original number, and we want to line up the decimal points. We want the repeating parts to line up. If they don't, something's wrong. So 999n equals 345. So then we could divide both sides by 999. And we could, I think, take a 3 or a 9 out of this. 3 plus 4 is 7 plus 5 is 12. So 3 goes in to the top and the bottom. So that would be 115 over 333. And I think that's as good as we can do. But that's also an answer. This one has repeating, but it only has 2 repeating digits. So we're going to multiply by 10 to the second power, 100. And that's going to move it over the decimal over 2 spots. And you could write the repeating part like that, but what we want to do is get the repeating part to be in the same spot as it originally was, so that when we subtract, they cancel each other out nicely. If they don't, then that's not going to work. So 34.2, there is a decimal there, which should not be in your final answer. So that's 342 over 990 if you multiply the top and bottom by 10. I think we get 3 plus 4 is 7 plus 2 is 9. So we definitely take a 9 out of both of these. So 9 out of 342. Well, it's almost 360, right? Which would be 49. So I think it's 38 nines over 110. Or no, 38 nines over 110, which we could then reduce even further, 19 over 55. So that's how you do those. Write an interval for each graph. So this is just practicing interval notation. There's no work to be done. These are answers, pictures of answers. And the way you guys used to write them was like this, right? But now, and sometimes we might still do that, but now most of the time we're going to write them like this, right? This would be x is greater than or equal to -2, but now we're going to say -2 to positive infinity, bracket, parentheses. So we put brackets on the solid dots, or equals to. And we always put a left and right boundary on interval notation. Now this one would be x is less than -3, or x is greater than or equal to -1 and less than 2 at the same time. So this is the way you would write it before. Now the way we're going to write it is negative infinity to -3. And then this is some symbols I'm going to show you today. Union -1, which should have a bracket on it, to 2 parentheses. So this is the new way of writing it. So union, that's a union symbol. It looks like a capital U. It's not quite a capital U, but I'll be talking about that notation more today. And then these problems are your algebra review. Now this is this is nicely already factored for you, all on one side, equal to 0, factored. And so those are your roots. So the thing is, this isn't a parabola like we were talking about before. but we're going to put the dots on here. So I'm not going to do the graphing technique. So that's where that graphing technique kind of falls apart, is when you get like much higher degree polynomials, sketching the graph isn't so easy. So we're probably going to do that testing method. Test x equals 3, test x equals 1 or 0, test x equals 4. So test a value in each region and test it up here in original. So if you plug 3 in here, it's going to be positive, which is false. If you plug 1 in here, there's going to be negative times a positive. So you don't really need to know what the number is. And testing in the factored version is the easiest because you can quickly decide, well, this is going to be negative, and that's going to be positive, so it's going to all be negative, which is true, right? And then if I plug -4 and that's negative, cubed is negative, and that's negative, cubed is negative, and negative times negative is positive, which makes this false, not less than. And so then here's your answer. And the way we're going to write it now, interval notation, would be like that. The way you would write it in previous years would have been like that. Now this one, we need to move everything to one side equal to 0. In general, when you're solving polynomial inequalities, you want to move everything to one side, standard form, compared to 0. Keep the symbol. And then factoring, hopefully, if you can factor, sometimes you can't factor, so you have to use like quadratic formula or something like that. But two numbers that multiply together to get -16, add together to get -6. That's going to be +2, -8. So x equals -2 and x equals 8. Now, this one, we could use that trick I was showing you guys yesterday that I liked to show my students how to do. Say, okay, put these on here and then say, okay, well, this is a parabola that's definitely opening up because the first term is positive. This is where the y would go. Y is greater than or equal to the parabola, so you'd shade up. And we're just looking at, though, where y equals 0, so it's just going to be -2 to 8. Or last year, you would have wrote -2 to 8 like that. So, but today, I'm going to show you guys I think I'm going to be showing you guys some new tricks on how to do this problem, because we're going to get much more complicated problems, and the graphing technique isn't going to work, and testing every region is a little tedious, and so we're going to learn a new approach today. So today's notes. Here. So we're going to talk a little more about interval notation. So this is a Venn diagram. This is our classroom. Everyone in the classroom. This is girls. This is drivers. This must be girl drivers. So, this is just kind of a visual way of looking at multiple inequalities together. So if we look for girls and drivers, that would be region C. And we call that the intersection of regions B and D. It's where they overlap. And the symbol for that is this like upside down looking, almost like capital U. And so that's how we do that. And then girl or driver would be everyone in regions B, D, and C, right? Because it could be these ones, it could be these ones, or it could be these ones. And so what we call that is the union of those regions. And we use this capital looking U, and that kind of makes sense for union. Now, union, just to help you remember, it's kind of like that's a fancy word for marriage sometimes, right? And so girl or driver, by the way, is not mutually exclusive, meaning it doesn't have to only be in one. It could be in both, right? So it doesn't have to be in one or the other. It can be in both at the same time. Okay. Now, marriage, union, you might think, okay, I don't know if, when two people get married, they have all their stuff, right? And it all gets combined. They both had a toaster. They both had a TV. Do they now only have one toaster and one TV? Do they only have the things they had in common and they only have one of them, like an intersection? No, they have everything they had separately, and they have it all together, the things they had in common, the things they don't have in common. They have all of that stuff, right? When you get married, you have lots of extra stuff. Now, you might choose to get rid of some of them, but so here's some exercises in trying to simplify some of these. So one is understanding what this means. So the U is union. Now, by the way, union is the same as or, okay? So you might try and remember that because that's the way you thought about it. With inequalities or conditionals, the word and has a different meaning than or. And requires they're both true. Or requires that either one or both are true. So this is union. So this is the same as or. Okay, it's all of these. Union is everything combined. Now, I'm going to encourage you guys, at least at first, to maybe draw pictures of these because I find it way easier if I draw pictures. So I draw, just visual representations of these. Now, I try and line them up at least roughly correct, at least. So -1 should be between -4 and +1, right? And +5 should be to the right. And I draw them above and below each other. And I say, okay, well, I want the combination of both of those. So that's going to go from -4 all the way to 5. And it's going to be everything in between. And that's your final answer. Okay. So I've just redrawn these in visual form. And this is my answer. Now, you need to write the answer in interval notation. That's -4 to 5, bracket on the -4, parenthesis on the 5. Now, it doesn't matter that -1 was an open dot here, because this one had -1 in it, and they don't both have to have it. Now 5 stays an open dot because the first one didn't have 5 and the second one doesn't have 5. So if it doesn't belong to both of them, then yeah, it's got to be open dot. But if one of them has it at least, then that's a solid part of your answer. So this one is the same problem, but it's intersection, which is the same as and. And so I would do the same thing. Just draw a quick picture. I find this makes it very obvious what the answer is, whereas sometimes it gets a little more complicated if I'm trying to do it in my head. Now, intersection means that they have to both include it, and that's this region here, and you could draw a picture of it if you want. I think the last picture isn't as necessary, but it's going to be this. And we're going to leave -1 out, even though we included last time, because -1 does not belong to both. But 1 belongs to both, right? So your answer is -1 to 1, parenthesis, bracket. This one, this is a open dot at 2, and arrow to the left forever. And this is an open dot at -3, which should be the left. Open dot to the right. This is union. So this is or. You get everything together. You just combine everything. Union, everything gets combined together, even if they didn't have it in common, and you get the solution looks like this. It's all real numbers, all reals, all real numbers, but the way I want you to write your answer is interval notation. So you're going to write it -infinity to +infinity. So visually it's the whole line. Okay, same example here, but we changed the notation in between. So I'm just going to redraw this picture real quick. And then it's intersection, which is the union one. I think is easy to remember because it looks like a U, and union's marriage. So the other one, the upside down one, must not be union. It's intersection, and it's and. So they both have to be true. So the answer is -3 to 2, parentheses. Oh, there's a bracket here, so that's supposed to be a solid dot. So there was a little minor difference here. So that should be a bracket because it belongs to both of them. So you're going to be doing some of that on today's assignment. You're going to have some examples like that. You're going to have some problems like that on your next test. Okay? So next problem, solving polynomial inequalities, which we started doing yesterday. And we just reviewed, the ways we had learned how to do it back in Algebra 1 or Algebra 2. And here's one that's complicated, and it's already factored for you, so that makes it easier. So, so where these equal 0, where the factors equal 0, is called zero product property. So it's going to be x equals 0, 2, and -1. So what we're going to do, I'm going to teach you a new way of doing this, okay? What we're going to do is we're going to make a number line, just like we were. We're going to put these in order. Now, these are all going to be solid dots because it's or equals to, right? Solid dots. And they need to be in order from left to right, smallest to biggest on the number line. And the way we were doing it before was we were either trying to sketch a graph, which is much more complicated now and not reasonable. And I'm going to give you even worse ones. Okay, and you're not going to want to sketch a graph, but we're still going to try and figure out the answers. The other way was to test every single region. Now, one of the things that maybe you realized on last night's homework is that when you're doing these, it seems like usually the regions alternate back and forth. They work or they don't work. So they use, and you might say, oh, okay, that's a shortcut. I'm not going to test every region. And actually, that's a good thing to observe. The problem is it's not always true. It is usually true, and we're going to take advantage of it. When it's not true, I'm going to tell you how to spot when it's not true. We'll be able to tell ahead of time if it's not true and be able to deal with it. So this is a shortcut. So we're just going to test one region. Now, I typically will test far right, okay? I think far right is the easiest. And you're going to write it in your work. Test. Tell me what you're testing. X equals 3. You want to test it in the factor version because, like I said, we don't really care what number we get. We just need to know if it's positive or negative to see if this is true or false. So if I plug 3 in, positive, everything's positive. That's why I like testing far right, because usually everything is going to be positive, and it's a quick conclusion. Because if you test somewhere in between, some are positive, some are negative. You got to keep track of how many negatives you have, and if it comes out positive when you're done. But if they're all positive, it's really quick. So that's going to be false. And then we would say true, false, true. Okay, that's usually how it works. But this one has an issue. Okay, test -2 in here. -2 to the fifth is negative. -4 to the third is negative, so that's a positive. -2 in here would be -1 squared is positive, which is false. So something went wrong there. Okay, everything else is correct. So generally it does alternate. Okay, now what happened here was that anytime you have a power, an even power on one of the factors, that one is not going to change signs. It's not going to, what happens is graphically, it bounces off the graph. Like that's a double root. And when a function has a double or even root, and that's an x-intercept, usually the graph will go through the x-axis at x-intercepts, but at that x-intercept, it turns around at the x-axis. And so, like if you had x plus 2 squared, that's a parabola, and it has -2 as its x-intercept, but then it goes like this. Instead of going through the graph and changing from positive to negative, it just stays above the graph. So it's a special case. And so then the sign isn't going to change, and the inequality isn't going to change its true or falseness. And so that's what we do is if they have an odd power, it's going to behave like normal. If it has an even power, it's going to bounce off the graph. So we need to be really good at this because I guarantee we're going to be doing this all year long with more and more complicated things. But these line check ideas are very common, very useful, and we need to be fast at these, okay? So if it has an even power in the root, it bounces off the graph, okay? And so there is no sign change, and so there's no change in the true or false. So it stays the same on both sides. So if it's false here, then it's going to stay false here. If it were true here, it would stay true here. And so from whatever side you approach it, it'll just stay the same. And then after that, it'll keep repeating. If it has an odd power, it goes through the x-axis, it crosses it, and then the function does change sign, and the inequality changes. But we only need to test one point, and I usually go far right. I would usually do one far edge or the other, but I'd usually go far right. So here's another one. Why don't you guys pause the video and try this problem yourself and see how you do, and then unpause it, and then I'll show you the work. So go ahead and pause it and try it. So this is even. Now what I might do is put like a little star next to it. Okay, this is odd, so that's okay. This one's even, so those are going to both have issues. So x equals 0, -1, and +2. But these guys are going to be the ones that have that issue. So you want to make sure you keep track of them, because a lot of times people identify them, but then they lose them. So these are going to be all open dots, because there's no or equals to here. So open dots. And they don't need to be spaced out apart, correctly. They just need to be left to right in the right order. Test a value. I need to know what you're testing. You're going to test one value. I don't want you to test any more than one value. I like far right for these kind of problems. Positive, which is true. Now remember, and I like to put these little stars next to these guys to remember, okay, yeah, the 0 and the 2, we're going to have this, so it's true, and then it stays true, and then it stays true, and then it finally starts alternating back to false. So it's true for all of these. Now, this is a picture of your answer, which I find very helpful. Then you still got to write interval notation. So the interval notation for the last problem would be 0 to 2 brackets. And then a lot of people just leave that as their answer. But -1 works all by itself. So we put in these little curly braces, and then we say union, because it's this or this, right? And here we would say -1 to 0, parentheses, union, 0 to 2, parentheses, union, 2 to positive infinity. This would be the answer I expect in interval notation. Okay, now interval notation is a lot quicker to write than the way we've used to write it before, and that's, I think, one of the reasons it's common, is it's easier to write. Okay, now there's one more problem on here. The back of this is your homework, okay, but there's one more problem here, which I'm going to bring back something that maybe you haven't thought about for a while, or it's possible you haven't done. But we would want to move everything to one side compared to 0. That's generally the best strategy here. And then you'd want to factor this. Now you might be like, okay, well, let's find two numbers, x, and -1 and -2. No, because this is cubed. So that gives a problem to us. We can't factor this. It is possible to use grouping on a cubic, but you'd have to have 4 terms, which we don't. We can't use quadratic formula because that's for quadratics. This is a cubic. And so this is not an easy one. Okay, now we should actually have 3 roots, because whatever the highest degree of your polynomial is, that's how many answers you should get. Now you might get some repeated ones. So how do we factor this? I mean, this is a big deal. So the way we do it is we use something called the rational root theorem. And if it's been a while, or if you have learned this before, you need to pay close attention. I'm going to put one of these on your next test. Rational root theorem. And rational root theorem says that if it has rational roots, it will be from this list of P over Q values, list of candidates, if it has rational roots. Now you're going to get a list even if it doesn't have rational roots. So this could be a losing effort. The P values come from the last number. Okay, it's all the possible factors, plus or minus 1, plus or minus 2, all the different ways you could get 2, a list of all the numbers involved. 1 times 2, -1 times -2, just a list of all. Q is a list of all those from the coefficient of the first term, which in this case would just be plus or minus 1. It's weird to me because it's P over Q, and I would think P would be the first one and Q would be the last one, but it's backwards. But I remember that my logic is backwards. And therefore, I remember to get it right. Now, P over Q is a list of all the possible ways of combining these. So 1 over 1, -1 over -1, 2 over 1, -2 over -1. Now, what's going to happen is it's just going to be plus or minus 1, plus or minus 2, because dividing these by positive -1 gives you plus or minus 1, plus or minus 2. So this is our list of possible values. So now what we have to do, one, we don't even know if any of these are going to work. Any of these might work if has rational roots. The way we test it is I usually just test in my head. I plug one into this, and if it is a root, it should give you 0. So if you plug 1 in, 1 minus 3 is negative 2 plus 2 is 0. That one works. And as soon as you find one, stop, because it'll be easier to find the other ones later a different way. But I usually just start with the easy, smallest numbers, positive numbers first, then negative numbers, and just try and find an easy one. But you just got to find one. Now, there might be another one here, but I'm going to just say, okay, well, I know positive 1 works. So that means that x minus 1 is a factor of your polynomial up there. Okay? Positive 1 comes from x minus 1, right? Positive 1 root comes from x minus 1 factor, because it would be what makes this 0. Now, with that in mind, we got to try and figure out, well, how do we factor that out? And there's two techniques. One technique is to use long division polynomials, which would work. But there's another technique that that does the same thing, but much faster. So what we're going to do is we're going to use synthetic division. So synthetic division is for dividing first degree binomials out of a polynomial. So it only works for this kind of case right here. And so what you do is you put the root there, and then you put the original coefficients. When it's all on one side equal to 0, it's 1. If there are any missing terms, you got to put 0 because there are no x squared terms. And then you put negative 3, and then you put 2. You don't put the x's and x cubes and stuff, but you just put the coefficients in order, and if there's any missing, you got to put 0. Okay, and it's got to be when they're all on one side equals 0. And then what we do is we drop the first term down, and then we multiply it by this number here, and we put that number here. 1 times 1 is 1, and then we add these, and then we repeat. 1 times 1 is 1, and then we add these, and you get negative 2, and then you repeat. 1 times negative 2 is negative 2, and then you add these, and you get 0. Now, at the end, you need to get a 0, okay? Because this is your remainder after your division process. And if the remainder is not 0, that means you didn't actually get the correct root out of it. You can do long division with polynomials and have a remainder left over, but that's not what we're trying to do here. Now, what we've done is we factored the x minus 1 out, okay? And what's left right here, these numbers represent the new polynomial inside that you get after you factor x minus 1 out. Now, when you factor, you're dividing, but you don't want it to disappear. Now, these are all going to be 1 degree less than what we started with. So the first one was x cubed. So now this one's going to be x squared because you've divided an x to the first out of it, right? So x cubed, blah, 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 divided by x squared, blah, 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 or x, blah, 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 is going to have an x squared term in it. So x squared plus 1x minus 2. And then we still have the less than or equal to 0. Now, we could do rational root theorem again. We could still go back to this list of roots. We could make a new list that's probably shorter using this p and this q, but this is a quadratic. So at this point, just factor this the normal way. That's going to be way easier. So we only use synthetic division rational root theorem when we really have to. And as soon as we get down to something that's easier to factor, then we go ahead and factor that just the easier way. So it's going to be plus 2 minus 1. Now, we factored the whole thing. Now, by the way, negative 2 was in that list over here, right? So we would have eventually found it, but then positive 1 happened again. So the thing to also watch about rational root theorem is that you might get the same root multiple times. Now, I'm going to rewrite this. X minus 1 is x minus 1 squared. It's a double root. And so remember that if they're to even power, they're going to bounce off the graph. So x equals 1 is going to bounce off the graph. X equals negative 2 is going to be normal. We're going to do a line check now. Solid dots because it's or equals 2, right? Solid dots because it's or equals 2 at negative 2 and 1. And this is going to be the one that bounces off. We're going to test one value. You got to write it down. I like to test far right, so I'm going to test 2. Positive, positive, which is false. But because this bounces off the graph, it stays false. And then it starts doing that alternating thing again. Your answer is negative infinity, negative 2, parenthesis bracket, and then union. Don't forget the 1. That's a solution. Don't forget it. Now, if that was an open dot, it wouldn't be a solution, right? So that's a little review or potential first time some of you guys have seen that. That's a rational root theorem, which gives you the list, and then synthetic division is the process of dividing it out. There's another process called long division, but this is a lot quicker. It's a split kind of shortcut. Your homework is on the back of this worksheet. So you're going to try all these tonight and do your best. Now, I want you, as much as possible, I want you to use the new technique for solving any of these, all of these. It says to solve graphically, but that means use the line check. 11 and 12, I just put it on there. I want you to see what you can try those out. Those are called rational functions. We'll talk about those more tomorrow, but just see what you can get. If they are linear inequalities, then just solve them the easiest way. But on any of these polynomial inequalities, try that new technique of doing the line check, but checking one spot and then flipping true, false. But watch out for the repeated roots. Now, you might need to use rational root theorem on like 1 or 2 of these problems. So you have a good opportunity to practice that. So try this today and check your answers online, and then we'll go over questions in class, or I'll post work in a video.